Good morning, everyone. Can you
Good
hear me?
morning.
Morning.
Yes, we can hear you, and we see thermal properties of matter.
Okay, good. Thank you. I believe we've all received the midterm 2 script. I sent the first one, but because it was marked on the newest version of PDF, when I save it, I didn't know that it was not saving this course. So I had to do like a print to PDF for everything. So I apologize for sending you that first script that had no score on them, okay? Okay, so today I want to look at the beginning part of the discussion on chapter 12 of our test, and that is thermal properties of matter. Now, in chapter 11, we started the discussion on thermal energy. We talked about heat and we talked about temperature. Okay, so we're just going to advance those three concepts as it relates to matter and how we use them to analyze the process of energy transfer in systems. Okay, we're also going to advance further to using it to calculate or quantify the thermal change in systems. The image before us is like the typical, we've seen this kind of image before, the thermograph with the red showing the area for higher thermal energy and the blue showing the cool areas. So we're looking at that. It is that thermograph experiment that actually led to most of the established principles that we're looking at today. So as usual, we'll be looking at major three blocks. First, we'll look at ID gas. And looking at ID gas, we'll be looking at the atomic model of matter as it relates to gas and the several state of matter. Then we'll look at heat and temperature. And we'll also be able to compute the temperature change that occurs when there's heat transfer. We'll also look at details of heat transfer and how the mechanism of conduction, convection, and radiation happens in heat transfer. But our main goal will be to use the atomic model of matter to explain the many properties of matter associated to heat and temperature. Okay, so in our previous classes, we saw system describing the macro states, but in this discourse, we'll be going beyond the macro states to having an idea of what happens in the micro states. Okay, so to begin our discourse, we want to look at the atomic model of matter. We know we have three basic states of matter: the liquid, the solid, and the gas. So when we see an expanded view of the particles of a gas, we see that first we want to make an assumption that we want to use the spherical shape to represent all the particles of these various models. Okay, so we see the particles of the gas, that they are spaced out, not fixed in a definite position, always undergoing a random motion, interacting with each other and colliding with the wall of the container. And their collision is majorly or basically elastic. Okay, we see that of the liquid. We see that the particles are closely packed. They are not in a definite shape, yes, but they are closely packed. And that's because they have a weak bond that exists between them that keeps them together. And it's such that when it starts flowing, they glide over each other that brings about the flow we see in the liquid. So the motion of the particle is not as randomly, though the motion is random, but not as that of the gas, because the space between them is closer than that of a gas. Then we'll see that of the solid here. The solid has a defined pattern. You can see the arrangement with the spring-like bond existing in between them here. These are the spring-like bonds. We have seen this kind of shape before when we talked about friction, okay? That how that friction, these bonds break to bring about a separation of two objects in contact, okay? So these are basically the model or shapes of particles in the various constituents of matter, like the liquid, solid, and gas, okay? So the idea of how the atomic model of these matter phases are arranged is what we'll be using to answer or tackle the issue of thermal changes and the properties that make up those matter. How that the temperature would depend on the properties that make up that matter. So we advance by looking at the atomic mass and the atomic mass number. Okay, atomic mass and atomic mass number, they are not new to us. We know the first 20 elements of the periodic table, and we know that we use their atomic number to know their position, but the atomic mass number is actually what we use to define or the measure of the substance that that element contains. Okay, so atomic mass number is simply the sum of proton and neutron, and it's represented with the letter A. And it has the unit U, which we call the unified mass. And sometimes it is expressed as the atomic mass unit, and sometimes as Dalton. But whichever expression, we can actually convert one of it to the other. Example, because it's talking about mass, sometimes we have the basic standard conversion that 1 U is equal to 1.66 times 10 raised to the power minus 27 kilogram. Okay, so we should note this because we usually apply it to calculating problems. Okay, so we know what our atomic mass is, and we know what atomic mass number is, and we know how to differentiate the atomic mass number from the atomic number. They are different, okay? Where this one is focusing on just the proton, this or A is focusing on the sum of proton and neutron, okay? So we're not really going deep into how we come about those numbers because we just want to remind ourselves of the atomic accounting so that we'll be able to apply them to solving problems that relates to matter. Okay, another thing we should remember is the definition of mole. Okay, mole talks about the amount of substance in a system. Just like in the macro system, when we talk about mass, to describe, using mass to describe the amount of substance that an object contains. That is how we use mole also in analysis. It tells us the amount of substance that a system will have. Okay, so we have that 1 mole of substance, which we approximate as 1 mol, 1 mole, has 6.02 times 10 raised to the power 23 basic particles. So if that is the basic unit of 1 mole of any material, then we can go from the basic to use the idea to have multiples of these to know the exact amount a substance will contain. So the number of the basic particle per mole in the substance is what we call the Avogadro's number. So this value is actually the Avogadro's number. Okay, and it's a constant value. it should be in your what do we call that equation? What do I call that sheet I used to give to you? It should be there as one of the constants that will be stated. Okay. So the Avogadro's number is stated in this value, but with the units per mole. Now, if the Avogadro's number defines the basic particle, what happens when we have multiple particles in the system? We'll have that the number of mole in a substance containing n basic particles will have the relationship number of mole, n being the total number of particles in that system divided by the Avogadro's number, and that will give us the number of mole in that substance. Okay, so we'll have on a periodic table monoatomic, diatomic mass. We're just going to limit ourselves to these two. All right. We're not going to look at the complex combination of monoatomic and diatomic masses. So we'll have monoatomic mass, that is elements that can exist in their single phase, and we'll have some that cannot exist on their single phase. They have to be pair, like oxygen will have to, oxygen is one of the most common diatomic examples we have, and also the nitrogen. Okay, so for such, we also factor that when we have their mass number, we multiply by 2 to have the exact value to describe the amount of substance such elements will have in a system. First part of this discourse is just to remind us about atomic accounting and the values or constants that we use to describe the atom, because we'll be needing them to solving some of the problems we encounter in terms of thermal energy transfer, thermal energy change, and heat energy transfers. So the molar mass, we have seen the mole, number of mole, we have seen the atomic number. We want to look at another important property to calculating atomic, determining atomic accounting, which is the molar mass of a substance. We use the symbol, we know M represents mass, we use the symbol MO to stand for molar mass, and the molar mass is always the mass in gram of 1 mole of substance. We know the value of 1 mole of substance, okay, which is given by the Avogadro's number. So the mass in gram of that 1 mole is what we call the molar mass. That is the molar mass of, for example, helium. We know the position of helium in the periodic table, and we know that its atomic mass is 4. The molar mass, the atomic mass is 4U. Therefore, the molar mass is 4 grams per mole. Okay, so but when we look at the atomic elements such as oxygen, that we know its atomic mass to be 16, we multiply, because it is 2 oxygen, 16 times 2 gives you 32 grams per mole. So we have to factor whenever you're given a question and they state the element, is the element a diatomic or monoatomic? Because that will define the value you'll be using to solve the problem. Okay, so we'll look at the number of mole in terms of molar mass. The number of mole that a substance will contain is therefore giving us the mass in gram over the molar mass. Molar mass is usually something we can always recall from our periodic table. Okay, so it's one of those established constant numbers for different elements in question. So we'll have the image here to typify what we've been saying. We see the 1 mole of helium, the big balloon here. We see that of 1 mole of sulfur, the yellow one, 1 mole of copper, brown, and that of mercury. Each of these substances, these are the display of their 1 mole volume. So let's quickly take an example to see how we apply this in solving problems. A system contains 100 grams of oxygen. How many mole does it contain? How many molecules? Okay, so oxygen first we know is diatomic. So we'll factor that its molar mass will be 32 grams per mole. So from this equation that we just saw here, that is the equation that says the mass in gram, sorry, this is mass in gram over the mole. That's what I wrote there. I know some of us will not see it. Mass in gram over the mole. We use that equation. Now the mass in gram is given as 100. And we know for oxygen that the molar mass is 32 grams per mole. So we just impute that into the equation. And we have 3.1 mole. And that answers the question of how many mole does it contain. Now we'll move on to the part that says how many molecules. How do you define the number of molecules in this kind of system? We'll have the relationship N equal to N over Avogadro's number. We've seen that before when we define the basic particle in a substance. So applying that to look for N, because that's exactly what the question is asking us to do, we just make N the subject of formula, which will become, we'll cross multiply the number of mole times the Avogadro's number will give us the total basic number of particles in this system. So doing that, we just did 3.1 times Avogadro's number, okay, which is 6.02 times 10 raised to power 23 to get this value here. So that's how we got this value. Applying this formula, this is given as we have discovered here, and this is a constant to arrive at this. Okay. So you see that problems like that, they are short, but sometimes we have to do some conversion, calculation, or understanding of basic atomic accounting to get the exact value we need. So we quickly want to remind ourselves what the volume is when we talk about volume. In terms of the microscopic system, is simply the amount of space that the system occupies. Same applies in macroscopic, but we'll have other details to describing the macroscopic. Okay, we know that the unit for volume is meter per second cube, and sometimes we are given volume in cm cube, especially when you're working in the lab. Most of your measuring cylinders are calibrated in cm cube. You have to do a conversion to meter. So 1 meter is simply 1 times 10 raised to the power 6, simply from 1 m being 100 cm and 3 length times breadth times height, that is volume, and that will give you 10 to 6. Okay, so in case whenever you're forgetting the conversion, you can quickly do that to recall how to take centimeter cube to meter cube. All right, so we'll move on to the second part of our discourse today, which is we have looked at the atomic model as it relates to matter, talking about its liquid form, solid, gaseous state, their particles, and how we describe each of those particles, to knowing the mass it contains or substance contained in such particles. So I want to quickly advance to looking at the atomic model of an ideal gas. Okay. Now, when we say ideal gas, we're referring to like a standard system or a standard gas system that we want to use to describe any substance that is existing in its gaseous state. Okay. So we see basically when we looked at the atomic model of matter, how that the particles of the gas, they are not closely packed, they are always in random motion, they can hit each other and also hit the wall of the container, and the kind of interaction is elastic. Okay, so that system is basically what we call the ideal gas system or ideal gas model. A model having constant random motion that interacts with each other, colliding in an elastic manner with one another. And because it's in a closed system, there is no loss in energy from the collision with one another or with the wall of the container. So we'll go straight forward to establishing the important facts, which is the relationship between the temperature and the kinetic energy. Now, because they are constantly in random motion, it means that some of them will be moving at different speed. So we'll have to describe their kinetic motion, kinetic energy in terms of average, because not all of them have the same speed. Okay, so the relationship between the temperature and the kinetic energy is given by T equal to 2/3, the average kinetic energy, over KB. KB stands for the constant known as Boltzmann constant, and it has a constant value 1.38 times 10 raised to the power minus 23. So if we make this the subject of formula in this equation, we'll arrive at this. Cross multiply divided by the coefficient of K average. That's how the flip came about 2/3. We simply made this the subject of formula. Okay. So now, seeing that the relationship between the kinetic energy is having a direct proportional relationship with the temperature, that is how this equation, or what this equation has pointed to us. Okay, so therefore, because we know the description of thermal energy to be the sum of kinetic energy in the system, we can therefore use this expression to define the thermal energy of the ideal gas containing the n number of atoms. Okay, from the definition of thermal energy, which is the total sum of kinetic energy, we now have that the thermal energy is actually equal to this expression because it is the definition average K. Just multiply the number of atoms, which is the sum of that total number. That is how this M came into this expression. So this, therefore, is the equation for thermal energy of an ideal gas with n number of atoms. Okay. So if there's a change in temperature of such system, which we have already established that a change in temperature will have a direct proportional relationship with the thermal energy, which is the average kinetic energy. We will have that change in thermal energy, therefore, will bring about change in temperature of that system. So that's how we have change in T. And we know that we can actually express this in terms of initial and final, but this one we can't because we know how we determine that by defining other definite parameters and saying what remains is thermal energy. Okay, so that's why we didn't have to break down this equation further to bringing in the initial and final. So we'll take an example. A large bathroom contains 1 times 10 raised to the power 27 molecules of air. If the model of air, if we model air as ideal gas, whenever we say that, you know what we mean, right? how much energy is required to raise the temperature of the room by 5 degrees Celsius. We know that whenever we're doing thermal energy calculation or change in heat as it relates to thermodynamics, we have to make our temperature unit to be in Kelvin. So whatever unit we are given that is not in Kelvin, we have to go first to convert into Kelvin. But from this question, we did not just have to go to convert to Kelvin. We had to understand that the statement here told us something about change in temperature. All right. And we have established that when we're looking at the scaling system of temperature, that the change in temperature on the Celsius scale is equal to change in temperature in the Kelvin scale. Okay, you saw those two, if you recall, those two temperatures that we mentioned, where we'll have the basic 100 value change in both ends. So knowing that the information provided to us is actually change in temperature, because we want to determine how much energy at this change in temperature, we simply did not have to do like a conversion to plus 2,3 value, but establish that information that at absolute temperature, the change in the Celsius scale is equal to that of the Kelvin scale. So that is how the change in temperature became 5 Kelvin. Okay, so knowing the value for temperature in Kelvin, we apply the equation, the last one that we talked about, the change, thermal change. And then we'll have our value of N given in our question. We'll have the constant, Boltzmann constant, and we'll have the change in temperature to have the final value as 100 kilojoules. So 100 kilojoules is the energy required to raise the temperature of the room to 5 degrees Celsius. Okay. So we advance further to reminding ourselves another important thing about molecular speed and temperature. So if we still keep the idea of the ID gas, which tells us that the motion are always in random, and we also know that each of the particles of an ID gas will have different speed, we put this in an histogram, as we can see here, putting the different speed of the particle of a gas in different bars. So we have different, the range of the speed for each particles falling within this range as represented in this histogram. So we did like the percentage of the particle and then their speed. We now discover that we have at a stage, if we want to understand the whole entire system of that gas, we have to, like we saw earlier, take the average kinetic energy, right? But in terms of speed, we have to bring in the concept of root mean square to taking the average speed. Okay, so we know that from the kinetic energy equation, velocity is a squared value. And we'll have to take the average speed, which is the average velocity of each of these particles. And because it's a squared value, that is what brought about the idea of the root mean square, which we'll be looking at again now. So the average kinetic energy, if we bring in that equation, this is the equation for kinetic energy, having a square of the velocity divided by the total number of the particle in that system. Now modifying this same relationship here, M will be constant. From your periodic table, you should be able to know the mass, atomic mass, and details of an element. But we see that the only changing parameter here now, this changes as well, but for a particular system is defined, but the speed, because it's a gas, is random, we'll have to take the average. So that gives us half m v square average. So to get the velocity for one, we have to take the root mean square, that is taking the the square root of V to have the single typical speed of one atom in that system. All right. So having established this, therefore, the equation of average kinetic energy can be rewritten in terms of speed expressed in the terms of root mean square, RMS. So if we express kinetic energy in this form, and we've already stated in our very first discourse that the relationship between kinetic energy and temperature is this, we can equate this with this. So equating 1/2 mv squared root mean square being equal to 3/2 Boltzmann constant temperature. Then you make this temperature the subject of formula in this relationship. You arrive at this equation. Try that out, okay? When you're reading, make sure you try it out to see how it came out to be this. Now, if you make V the subject of formula, this one, in this equation as well, we will arrive at this expression that we'll call the root mean square speed of an atom of mass M in an ideal gas at temperature T. Okay, so we see the relationship between the speed and the temperature. The relationship is such that the velocity will change with respect to the square root of the temperature. So take an example. Example 3 now. Most of the Earth's atmosphere is the gas nitrogen, which consists of, it's a diatomic molecule, okay? At the coolest temperature ever recorded on the Earth, which is minus 95 degrees Celsius, what is the root mean square speed of the nitrogen molecule? That is the first question. And the second part of the question says, does the temperature of the Earth's surface ever get high enough that a typical molecule is moving twice the speed obtained here? And they gave us the information that the highest temperature ever recorded on the Earth is 54 degrees Celsius. Okay, so we see that this question did not typify change in temperature, but it mentioned the various temperatures, so we'll have to convert to our basic unit Kelvin. So keeping that in mind, we begin solving our problem by defining or determining our mass for such system. So we'll have the nitrogen is diatomic and the atomic mass is 14 U. So because it's diatomic, 14 times 2 is 28 U, and the unit for U is this. So we did 28 times, that's 28 U times this to give us this in kilogram to express the mass of that substance. Okay, so taking this value to kilogram, we'll multiply 28 by this to get that. We did our conversion for the first temperature, which is minus 95 plus 23 to give us the value in Kelvin. And we did that also for the highest temperature ever recorded. So this is the coolest ever recorded, and this is the highest ever recorded. The first question told us to look for the velocity of the root mean square velocity. And substituting that into the formula directly, since we have all our parameters, it multiplied out to give us 400 meters per second. And the second part says, will the Earth ever get hot such that the speed of nitrogen particle will be twice this? Will it ever happen? So if at the least temperature, this is what we have, what will happen if the Earth gets to its peak ever recorded? We just did the ratio comparison, and we see that the ratio is 1.8. So it will never get to twice the computed speed. Okay, it's not going to. That's the comment to answer that question, is that it cannot get hot such that that particle will move twice the velocity at the root mean square velocity. Remember, root mean square velocity is actually the typical velocity that one particle of a gas will have. Okay, so another thing we use to describe the ideal gas system is pressure. Pressure, the concept of pressure defines, as we know, or we have seen pressure, no power, that's power. Pressure is represented with the small letter P, power with the big one, capital P. So pressure is simply defined as force per unit area. Okay, and we know that the pressure in a gas is actually influenced or determined by the collision motion of the gas with one another and with the wall of that container. So as it collides, as you can see in this image, typically we brought out a magnified one collision for one particle. It collides, it exerts a force at a definite area on that container. Okay, so we said the pressure is actually the force per unit area at that point. So we have the unit for pressure to be Pascal, and Pascal is simply a derived unit from Newton meter squared. Newton for F, meter squared for area. Okay, so to determine the net force, that is the net force for the pressure system, the net force depends actually on the pressure difference in the system. Okay, so we'll see that the system with a defined area A, the force acting and the one opposing it is typified by F1 and F2. So therefore the net force is going to be F2 minus F1. Remember, I said net force depends on pressure difference. So the difference in that, if we make for P equal to F over A, if you make F the subject of formula, it's going to be pressure A. So the difference in pressure is actually what determines the net force. So you have also that it will be the pressure on the 2 minus that of 1 multiplied by area. The area did not change. So bring that out, get the difference in the pressure to give you the net force. Net force, therefore, is equal to area multiplied by change in pressure. So let's see how that applies to in example 12.3. Patient suffering from decompression sickness may be treated in a hyperbaric oxygen chamber filled with oxygen at greater than atmospheric pressure. A cylindrical chamber with flat end of 0.75 meters. The diameter is 0.75 meters. Is filled with the oxygen to a gauge pressure of 27 kilopascal. What is the resultant force at the end of the plate of the cylinder? Okay, so we use the understanding of the pressure system we just looked at to calculate this. First, we can determine from the information provided the area. Area of a cylinder is simply pi r squared. The diameter of that cylinder is given. So we'll have diameter radius to be equal to 0.75 divided by 2. And that's how we got that value, 0.375 here. So taking the square of that and multiplying with the constant value of pi, we have the area to be 0.442 meters squared. Now bringing this into the equation, the change in pressure is given to be 27 kilopascal, which brought about the 3 zeros here. The kilo here is 1,000. Okay, so we'll have that the net force in this system will give us 12 kilonewton. So that's how I apply that to the equation. Sorry, I have to move fast. We still have so much to cover. So we've looked at the ideal gas model. Let's look at the kind of law that governs the motion of such system. We have been applying some of these laws, but we have not really brought them forth and stated them as law. Okay, so what defined the law that governs the ideal gas system? We looked at the ideal gas. We see that we have scenarios where if you increase the temperature, the speed tend to increase, like we have in these two bursts. We have also a scenario where you can actually increase the collision rate by decreasing the volume. You see the spaces between each of them are reduced, so they will collide more in this case. So we see that decreasing the volume of the container means more frequent collision. Therefore, the pressure in that system is increased. Why pressure is increased here with the increase in temperature, pressure is increased here with the decrease in volume. Okay, so we'll have the third scenario where we actually increase the number of particles without touching the volume nor the temperature. So we'll have the three parameters that we're playing with, which is the V, and we'll have the T, and we'll have the P. So we are defining this by changing the volume, changing the temperature, and increase in the number of particles. Okay, so if we can actually manipulate these three parameters to vary the condition of the gas, then there must be a law that applies these three to bring about what we see as a change in such a system. It is such that the pressure will be proportional to the temperature. That is the first case. We also have that pressure is going to be proportional to 1 over the volume, because you reduce the volume, which is the second scenario we saw. The last one, which is increase in the number of particles, pressure being proportional to the number of particles. So these three ideas is actually what define what we call the ideal gas law. Okay, so we'll have, putting these three together, the expression that pressure, in this case, directly proportional to T, inversely proportional to this, and directly proportional to the number of particle C, bringing in as a constant of proportionality. So if you look at this expression, actually, it looks like the expression we've seen before when we defined the temperature ratio with kinetic energy and we brought in Boltzmann constant. So C here is actually standing in like the Boltzmann constant. Okay, so if you make this the subject of formula, is going to be PV equal to C N T. If C is actually standing here like the Boltzmann constant, we can actually replace it with the value Boltzmann constant, since that is what is already established. So we'll have the first law expression, version 1, expressing it in terms of the Boltzmann constant, and version 2, expressing it in terms of the number of particles, representing, that's R, representing the gas constant. Various gas have their constant value. Okay, no, gas constant, not various gas has a constant value. Gas constant R, which is giving us 8.31 joules per mole times Kelvin. Okay, so the whole expression is what to explain here with the parameters given. We don't have time to look at the example, but please study this example. It's a straightforward one, and if you have any question on that, reach out to me as well. So we quickly want to look at the last part of the class within the next 7 minutes, which is the ideal gas processes. Okay, we'll have several processes describing the ideal gas, which we will look at, but we'll have the basic property of these processes. The basic property of the ideal gas process is that the quantity of gas is fixed. Okay, so we'll have that no air is added or removed for a system. If you consider a system like your tire, you fill it with air, it's running, you're using it on the road, there's no change. You're not stopping to say, okay, except you have a case where the tire deflates, you add air. But at the state where you sealed it and you can set it in motion, it has fixed quantity of air. And the initial state can actually be well defined. And we use the description, pressure, volume, and temperature to define the initial state. And also the final state can be defined as well. So if in such a system where we have the ideal process, we will have that the process property is actually PV over T equal to NR, which is constant. We got this expression from the equation of the ideal gas we have seen here. Okay, just make NR is subject of formula. That's how we got this. So this expression simply means that the pressure, temperature, volume of an ideal gas is constant, it's unchanging. That means if you measure it at the initial, you use it, measure it again, you will have the initial state being equal to the final state. Okay, now saying that this is equal to this is simply buttressing the idea of conservation, the conservation law. Okay, but we actually can vary each of these parameters depending on the process we are considering. So we'll have 5 basic processes. A process where the volume is kept constant, that is the final and the initial volume is equal. We'll have process where the pressure is kept constant. We'll have that where the temperature is kept constant. And then we'll have the thermodynamic ideal gas process. When we say thermodynamic ideal gas process, we're looking at a process where the first law we talk about E equal to H plus W, and then the second one where we talk about the change in the energy system. Okay, so it means for that process, you have to consider the thermodynamic first and second law and how they relate to energy transfer. So we'll have the fifth one, which is the adiabatic process. So we ought to look at them detailedly, but let's quickly do a summary of what we mean. For the first one, which is the process where the volume is kept constant, we see the pressure gauge, heat is added to the system. At the initial, no heat is added, the gauge is just a little bit above 0. The volume is constant. All right, but when you added heat, the volume did not change, but the pressure increased. So we'll have what we call the PV diagram. The PV diagram is simply the diagram that typifies the pressure, volume, and temperature expressed in terms of graph. We'll call it PV diagram. Okay, so you see it appears like the plot of pressure to volume. We see that volume is constant, but pressure is changing. So we'll see the process of constant pressure change. We call such the isobaric process. So we either say constant pressure processes, or we just simply say isobaric process. In this process, we said that the pressure is kept constant. The initial and the final pressure will be the same. So there's no change in pressure, but there is change in volume. As we can see here, the piston can shift, but the total pressure of that system is the same because pressure is defined from the net force, the influence of the external pressure on the internal, they are still the same. So regardless of the position of the piston, the pressure is not changing, but the volume or the space is changing. And we can see that as well in example 12.7. So the next, which is the constant temperature process, which we can easily call the isothermal process. And that means temperature is kept constant. And for such system, if you keep this temperature constant, as you can see in this diagram, you can actually increase pressure by alternating the volume. Okay, so you see that P, pressure in such a system, is inversely proportional to V. And that is why we'll have the kind of parabolic curve here, the hyperbola curve here, to show the curve that stands for inverse proportionality. Okay, the straight line like this stands for direct proportionality. So we'll have that at different temperature, the PV curve for the relationship of pressure and volume is going to take the shape of the hyperbola, this shape. So have the thermodynamic of ideal gas process that talks about or factor the work done by the gas. What happens if there's a shift in this kind of system? The piston took a distance. Yes, the volume can change, the pressure can be kept constant, but what will happen? Is there any kind of work done? Can we describe the pressure of that system? Work done happens majorly when there's constant pressure process. So the ideal thermodynamic process for ideal gas is working on the corridor of constant pressure. Okay, we describe the work done under the system of constant pressure to understand that process. So we have several facts that is put into place to understanding the thermodynamic. This fact is actually unique to the thermodynamic ideal gas processes. Okay, highlighting the facts, we're saying it's happening at a constant pressure. It's the equation only apply when we measure temperature in Kelvin, and the work done by gas is going to be positive when there's expansion and negative when the piston goes down or contracts or decrease the volume. Okay, so we therefore calculate such system by taking the area under the curve as the work done. Okay, so see example 10 buttressing that. And the very last one, which is the adiabatic process, is simply the process where the heat change in the system is kept constant. Q is equal to 0. So for adiabatic expansion, the temperature of the gas goes low, but when it compresses, the temperature of the gas increases. So that's how we control the pressure without change in the heat or temperature of that system. Change in the heat of that system is kept constant, but we use that to modulate the temperature without applying heat per se. So we simply change the temperature of a system, increasing or raising it by compressing or expanding the gas. Okay, so a adiabatic process is a system with no heat exchange with the environment. Okay, it's a long one, right? And I've just been talking. Please, I'll encourage us to look at these examples that I'm putting here whenever I say study this. And if you notice when we discuss any chapter that I'm emphasizing study example, I usually don't give us extra assignment on that because I expect that the activity you are to do or assignment you are to do is to study this example, and I expect a feedback. Just like somebody was asking about assignment 6, that they've not gotten the feedback. Everything in assignment 6 are examples in chapter 6. We have 12 examples to look at in chapter 6. And I just said, turn in the odd numbers, just to be sure at least you did half of what you ought to do or what you ought to have done. Okay. And I was surprised that most of us will still put what is not. That means we're not actually opening our textbook to compare what we look at in class to what is actually in the test. If there's an assignment, if I have to copy this out without saying it's example 12.5, many of us will give me solution that is not, which you ought to check the textbook, see first if it's there or not. I'm not bringing anything that is outside the test. Okay, and I'm not going to look at all the problems behind the chapter to say, okay, let me see, just take. It's something related to what we did in class that applies. Okay. If you have any question and the time is gone and you want to ask, just send me a mail, contact me, arrange a meeting with me, and we're able to talk it through. Okay. Any comments so far?
Nope, sounds good. You definitely went through that quickly though.
Yeah, it was a fast one, I know. Okay, I just needed to make sure we cover what we ought to have covered for the first class. All right, thank you so much. You can have a good.
Question.
Yep.
For assignment 11, where do we submit it?
Mhm. You said?
Where do we submit assignment 11?
Yeah, the assignment 11, I put it there that we are to turn it in on the due date on that post hole by the lab. Okay. Yep. And let me see what we have in chat here.